No, 0 to 4.
Right? When it's going from 0 to 4, the first one was negligent. Why? Because the 2, right, the first 2 on the other summation had already taken care of that full rectangle. There was no extra piece up here to add to it. But now there is. Right? The black rectangle goes above the bottom larger rectangle. You guys know what I'm saying or not?
You're adding.
Now that you made a line where it makes sense.
You see it?
Yeah, you're just adding the
I'm
triangle.
adding this little black thing. That little black brick, that little square, which it's a 1x1 square, right? Is that the first one? When I is 1. 1x1 square, what's its area? 1. So when I is 1, that's that first little square adding up. What's the area of the next black rectangle that's above the red line? 2. It's 2x1. When I is 2, you're going to get that one. Right? And when I is 3, you're going to be adding this one. Right? Its height goes from 2 to 5. That's 3 units by 1 unit is 3 and 4 and 5. And that's what this is adding up now. Yeah. Thanks for Lars pulling.
And so I'm assuming your time to the left and the right endpoint approximations aren't the same?
They should not be in general. Should not be in general. So that's our right endpoint approximations case. And again, it's an overestimate. So the actual area under the curve must be between 20 and 25. So as we know, this one was a complete underestimate. This one's a total overestimate. It must actually be something in between.
2 point.
Which we can easily compute because it's triangle and rectangle. But we don't need to. That's not the point. What is it? 22.5? That's what you'd expect, right? So get me right in there. I don't know. 22.5. Probably. I mean, it should be. I mean, this one underestimated by 5 of them. 1, 2, 3, 4. Yeah. Yeah, it should be.
Could we say one sigma I to 0 equals those boxes on the outside?
Yeah, that is what I'm saying.
So like we could find the individual value of I by like that function by itself. Do you see what I mean? If we find the value of 1 sigma I equals 0. Do you see what I mean? And then you can use that as your starting point. We figured out the value of all those squares put together.
You say without using the sigma notation?
Yeah, well, I mean, you'd have.
You're like avoiding it, or?
No, I'm just saying, like, you'd have start off point rather than not having a start off point. Do you see what I mean? Because the value of I is all those boxes that are up there. So you only
in this case?
Yeah, so in this case, we find I by itself, and then, like, do the sigma notation where it would be like 1, 2. Do you see what I mean?
The sigma notation is 1, 2, 3.
Yeah. So that's what we did.
That's what we did. Yeah. But in other cases, not just going to be as simple as 1, 2, 3. It's only because each of these is just an extra box extension, right? Here's the area 1, here's the area 2, here's the area of 3, here's the area of 4, here's the area of 5. But that's only because we have a line here. If this thing was curving anyway, you wouldn't have boxes. You wouldn't have perfect boxes sitting there, perfect squares sitting there.
Because that's like, that line is a constant line. It's
correct.
So
it's
like,
making the problem overly simplified.
Yeah, so the slope remains constant, like when you have different.
Right, exactly. Whereas you have a curve, what's the deal with the curve? Why is it curve? Because the slope's not constant. So that's going to make the problem a little more tricky. But the point is that you're able to follow these formulas. That's the main thing. You follow these formulas. I hope so. We'll do one more. We'll do a curvy one this time. X squared minus 1.
What number?
1 second. 17. F of x is x squared minus 1. It's on the interval 2, 4. And n equals 4, it says. I'm trying to keep the n's low in the examples so we don't have to do too many computations unnecessarily, waste too much time doing it. Sketch the graph of the function on a given interval. Okay? You guys know what x squared minus 1 looks like, I'm sure. If not, I'm going to just flunk here. So x squared minus 1 should be the standard parabola lower than 1 unit. So there's its vertex, that's a negative 1.
Can you erase all that other stuff?
What stuff? The red stuff?
Yeah. Distracting.
Sorry. Anyhow, yeah. Whatever you need, right? So where are the roots of this quadratic?
1 and negative 1, but only 1 is our.
So we're going from 2 to 4, right?
Yeah.
So let's just actually plot those points then. So 2, 3, 4, make it look better. All those people, hold on a second. What did they do before? So there's 2. Okay, I was thinking 4. Okay, so at 2, what's the function value?
Right.
Yeah, we have to scale this thing a lot. Are you serious, man? You sounded dead serious there for a second. Like that was really going to impact you somehow. And so I need to get up to 15 apparently. So we'll just go by 5, 10, 15, 20. All right. So when it was 2, you said it was 3, so that's approximately here. And when it's 4, it's 15. That should be exactly across the that tick mark there. All right, and it goes through 1. We've heard. And there's our part of the parabola we need. Of course we did, right? I'm not going to go through the whole thing. I just want to demonstrate this one more time. So we have 2 obvious subintervals, but it says n equals 4, so we need 4 of them. So we have to cut each of those in half. So it's not exactly the same as the what's that called? Scale. So there and there. Sketch the graph of the function. Okay, we did. Calculate delta x. No big deal. Delta x is 4 minus 2 on 4. Should be a half, which makes sense. You're going from 2 to 4 with 4 steps, each of them being a half. So that works out well. Delta x computed. And the grid points x naught through x in. So the grid points, A is x naught in their terminology. So that's 2. So there's the first one. And what's the second one? What's that grid point? I know the 3 here, just to be obvious. So 2.5, was that 5 halves? 2.5? 5 halves. And then what, 7 halves? There's our grid points. That's the terminology we're using in the textbook. Grid points. Okay. They use x naught for A. Apparently. It's sometimes. We did this problem. Got that mapped on there. What else? Illustrate the right Riemann. These are called Riemann sums. Illustrate the right Riemann sum. Okay. Everything we've been talking about are called Riemann sums.
And those are the endpoints?
Say one more time.
And Riemann sum of the endpoints?
Riemann sum is the whole thing. Illustrate the Riemann sum. So if we're illustrating the Riemann sum, that means draw the rectangles, basically. Draw the rectangles, superimpose them on the picture. So we said I'm going to use right endpoints. We did a right endpoint problem. Riemann sum, right endpoint this time. So it's right endpoints. That means the 5 halves is the grid point which determines the height of the first rectangle. So we'll